So first of all, I want to thank the organizers for the invitation and especially Sasha also for giving me the opportunity to talk here. So I will talk about aspects of Anderson localization with cold atoms. And so actually, there's no Majoranas around, no topological Anderson insulator, no many-body localization. So it's all very simple single particle Anderson localization that I'm going to talk about. So of course you can then ask what is still interesting about single particle Anderson localization. I think from experimental side it's quite clear that cold atom systems provide us the opportunity to really study Anderson single particle Anderson localization under rather ideal conditions. Now from theory, what is still interesting about single particle Anderson localization, I can just give you a personal answer to this, and this is that there has been one experiment which was studying the onset of localization, was I think quite a nice experiment. It was clear that with this experiment you should also be able to study signatures of strong localization. However, this signature was not really fully understood, and that was where we got interested in to really try to see if we can make some progress there. So that's one story that I'm going to tell you about, and the second story is that, well, once you looked at the experiment, you could actually realize that by small modifications, you could, just a very simple idea, you could play around and get some scheme how you can systematically also study the onset of Anderson localization, just given the great tunability of cold atom systems. So that's the second story that I will talk about. So and this is work done in collaboration from Theo with Alex Saltland and Kurt Müller. And then in the second part, we had exchange with Vincent Joss and Alain Spee from the experimental side. So, well, the motivation I already gave. Well, cold atom systems provide us with large tunable system parameters. So you have typically full control of the trapping potentials, which allow you to design the lattice geometry, effective dimensionality. You can design your random potentials by speckle disorder. You can tune the interactions, so that's all very interesting. And then the second aspect also, which is very favorable, is that these systems come very close to what is a closed system, so where you don't have to care so much about decoherence from a coupling to a bath. So there are recent examples, experimental examples which show this. So there's one very recent work studying the robustness of the localized phase under interaction. So I will briefly comment on this, although, I said my main focus here is on single particle physics. So it's a very nice experiment which for the first time really clearly studied the Anderson transition, which was in a dynamical driven system. And then there is this experiment that motivated us to start looking into this and the modification I was talking about, where you can generate some kind of echoes. So I will explain this in detail. So then let me come to the outline. So I will first give an introduction. So as this is an introductory talk, I will repeat some basic things about Anderson localization. So I hope I won't bore you with this. And I will briefly comment on some experiments with cold atoms that I found interesting. And this will be quite superficial, so I'm not really an expert on cold atoms, but I'll try to present a basic idea there. Then I will turn to this experiment, which is called here quantum quench experiment, which actually motivated us to then look within this experiment for a signature of strong localization, which appears here as a forward scattering peak, and then the modification of this already existing experiment by a simple idea which allows you to study the onset of Anderson localization, which we call it an echo spectroscopy. So let's start with the paper by Anderson back in the 50s that started the field, absence of diffusion in certain random lattices. So what is Anderson localization? Well, it's a single particle wave function in a macroscopic disordered quantum system can be exponentially localized. So to explain this or illustrate this, let's consider a simple 1D Hamiltonian where you have hopping between nearest neighbor sites and you have some on-site energy. So if this on-site energy is just fixed it's the same on all sides, well, then you have a periodic system. So the eigenstates of this Hamiltonian are just given by Bloch waves, which are extended. Now, the observation is you start to shift randomly these energies, these on-site energies, you disorder your system, and what you find is that the eigenfunction of such a Hamiltonian are now exponentially localized in space, where then the localization length appears as a characteristic length scale over which this wave function envelope decays. Now, this has been put into more systematic picture by the gang of four, basing on a simple single scaling parameter hypothesis, which states that if you look at the conductance of a system where you rescale your linear scales, this conductance should be just a function of the conductance of the original system. So this is equivalent to saying that the beta function defined here, where G is the dimensional conductance, so conductance is measured in some natural units, is just a function of the conductance itself. So if you take this as granted, you can look at the beta function in two limits. So on the one limit where you have just ohmic good conductor, there you find that the beta function is just a constant depending on the dimension of the system. So it's given by d minus 2. So in 3 dimensions 1, 2 dimensions 0, in 1 dimension it's minus 1. And then you can look at the beta function in the insulating regime where you have exponential suppression of the conductance. You find that the conductance, that the beta function is negative. Now, if you assume that the beta function doesn't do anything weird in between those limits, you just smoothly interpolate these two limits by a monotonic function, you find that the beta function is always negative in 1 or 2 dimensions, which means that as you increase the length of your system, you will always flow to the insulating fixed point, while in 3 dimensions you actually have a critical value of the conductance. If you are above, you will flow to a metallic fixed point when increasing the system size, while when you're below, you will flow to the insulating fixed point. So from this, one would conclude that all states are Anderson localized in dimensions smaller than 3 in an infinite system, and I should also say temperature equals to 0. So the important point here to make is that this localization actually is driven, or in low-dimensional systems, it's just driven by arbitrary small potentials. So, of course, you have a characteristic length scale, which is the localization length, but even if you have very weak disorder, you just have to make your system long in, or large enough in dimensions 1 or 2 to enter into the localized phase. So it's very different from, let's say, classical trapping, where you have random potential whose strength is of the order of the energy of your particle, and you can just get stuck in minima of your disorder configuration. So a different way to state this is that you can compare the motion of a classical particle in a random environment with that of a quantum mechanical particle. So classically, if you put a particle into some random potential, this will just scatter of your disorder. So it will just perform a random walk where the mean square distance propagated in time linearly increases in time, where the proportion defines the diffusion constant. And so this is just a random walk, which is a Markovian process, where the particle, after each scattering event, just loses the memory of the initial state it started from. Now, the observation by Anderson is that if you look at the same problem taking into account, quantum mechanics, something new enters, that is, well, the wave, the phase, let's say, of your wave package, which means that the particle now can interfere, meaning that the system keeps some memory of the initial state, and this then can lead to the observation that the mean square distance propagated in time saturates to a constant in the long time limit, so you have absence of diffusion in certain lattices. So to explain the microscopic origin of localization, it is convenient or let's say, to see what drives localization, it's convenient to go to the onset of localization. Let's say we have here a disordered two-dimensional system where now the size of the system is smaller than the localization length, and you can ask for the probability to propagate from one end of the probe to the other. Well, Feynman tells us that we have to sum over all the amplitudes, so we have to sum over all possible paths. A particle can go here from A to B, and what we sum is the amplitude, and then we have to square this. Now, here we are typically interested in system sizes much larger than the wavelengths of the particle, so the typical action associated with propagation along a given path is much larger than h bar, which means we can look at this then in a semi-classical limit. So in this, the probability to propagate from A to B is given by two terms. So the first is a sum over all classical paths, where what you sum is the probability to propagate along a given classical path. So this describes just the classical diffusion. And then you have an interference correction to this classical contribution, which is a double sum over different classical paths with the same action. And now the question is, well, what are then the relevant classical paths that drive you into the localized phase? And the answer to this is that it's self-intersecting path, in which exactly depends on the symmetry of the system you look at. So we can distinguish the three Wigner-Dyson classes characterized by the presence or absence of time reversal or spin rotational symmetry. So in the simplest case, in the orthogonal class, you have time reversal and spin rotational symmetry. Well, there you can have, for example, just a simply intersecting path. There now you can propagate along this loop in either direction. While propagating in either direction, so in clockwise or counterclockwise corresponds to two different classical paths. If you have a time reversal invariant system, then the phase accumulated while propagating along either direction, this loop is identical. So you have this singly self-intersecting path, which then gives you an interference correction to the classical diffusion. And this, of course, just expresses a tendency of a particle to return where it started from. So this expresses the localization, and this is driving localization then in the orthogonal class. Now, if you break time reversal symmetry, there is no guarantee that the phase accumulated while propagating along this closed loop in the one or the other direction, the phase accumulated is the same. So you don't get a quantum interference correction from the singly self-intersecting path, but then you can look at, let's say, a higher order where you have a twice self-intersecting path. Now here, a particle can propagate first, let's say, along the downer loop and then the upper loop, or along the upper loop and then the downer loop. The total phase accumulated while propagating through both of the loops, well, doesn't depend on the order. So meaning that here again you have two different classical paths with, which have the same action. So this is then, the two loops are then the driving paths which lead to localization, which will drive you to localization in the unitary class. Now if you still then consider, let's say, time reversal invariant system, but where spin rotation symmetry is broken, so you have spin locked to your orbital degree of freedom, then you can just see that, well, once you transverse this loop, the spin will flip, and this will just lead to an overall sign change in the return probability, meaning that instead of localization, you will have anti-localization. So you can make this more formal by looking at a perturbative RG of the beta function in 2 plus epsilon dimensions, and at the onset of localization, where T is now the inverse conductance of the system. So this is a small parameter in the game. And then, I mean, just making the analysis, you find these results for the beta function at the onset of localization in the three symmetry classes. So the first term just is the ohmic contribution in 2 plus epsilon dimensions, and then you see you have the leading contribution in the orthogonal, in the symplectic class with a different sign, and then in the unitary class you start with the beta function in the next order. So this is then the beta function that you find in the three symmetry classes, so you drive your system by increasing the size of your system orthogonal in the unitary class directly to the strongly localized regime. However, on different scales, so the localization length in the orthogonal class is smaller than in the unitary. Now, in the symplectic class, you first have a delocalization, meaning that you also have a critical value of the conductance. When you're above, you flow to the metallic fixed point, and below you flow to the insulating fixed point. So this is all what you get from, let's say, a systematic study of the onset of localization, where you have a controlled way to study interference corrections to your classical diffusion by just a small parameter, which is 1 over the conductance. Now, once you enter really the strongly localized regime, well, then in principle, all self-intersecting paths of all loop orders contribute. So in some way, you you don't have a controlled way to do perturbation theory anymore, and you really enter in the non-perturbative regime. So this was a very brief review of Anderson localization. So now, just superficial brief review of some cold atom experiments that I found interesting. So first there was quite interesting work in the group of Alain Spee, which is on the strong localization. So this was putting cold atoms into 1D waveguide, so with an initial density well localized, and then letting expand this cloud of cold atoms now in this 1D waveguide in the presence of disorder. One could observe that as time increases, this initial well-localized density spreads, but then freezes into a density profile, which really shows here the exponential decay. So this is, I think, quite nice, because it really now allows you to directly observe the exponential localization in the experiment. Now, there has been, I think, a very remarkable experiment on the Anderson transition, which was done recently, using instead of 3D disordered system, a periodically driven or quasi-periodically driven system. So this is a quasi-periodic kicked rotor, where you have a particle in 1 dimension, so it's a kinetic term, and then you give the particle a periodic kick, whose strength depends on the position of the particle. So let's first consider the case where this epsilon is 0. So you just give the particle periodic kicks. So this can be actually shown, this model, to be equivalent to a 1D disordered system, and this is experimental data in the late 90s, which now shows the localization in this kicked rotor model. So here, however, now you have localization in momentum space. So here's the mean squared distance in time in momentum space, and well, if you would have diffusive dynamics, you would just have a linear increase here, but you see clearly in the experiment you have a saturation to some constant value, so you have localization in this kicked rotor with single driving frequency. Again, here you see the intensity which has this exponential decay here, momentum space. Now, there has been then a very nice generalization of this kicked rotor model, which is now, let's turn on the finite epsilon. So what you have here now is you have 3 frequencies by which you drive the system, which are, however, incommensurate. So driving this 1D system with 3 periodic incommensurate kicks, one can show this is equivalent to a 3D disordered system. So this means now that in this, when you realize this system, you can actually really study the Anderson transition. So and this is now, again, experimental data for finite epsilon in this experiment. This is a very nice experiment in 2008, where you see for different parameters values of k and epsilon. So once you just have the linear increase of p squared in time, which is the diffusive regime, then you observe another regime where you have localization, and also they can tune the system into the critical point where you have now anomalous diffusion where the mean square distance here increases with a characteristic scale of 2/3. So they can then map out, depending on the two parameters, the phase diagram, and they can tune really into the Anderson localization, the Anderson transition regime, and there study then the critical exponents, so the localization lengths on the one side and one of the diffusion constant on the other side, and they find really very nicely agreement of the critical exponents, what one should expect from theory. So this is, I think, the first really clear study of the Anderson localization transition, of single particle Anderson localization transition. So this is quite remarkable. So then the last experiment I just want to briefly mention because I think it's very interesting, but as I said, doesn't really deal with what is the topic here. So this is a system with tunable interactions. So this is a very recent experiment in the group of Emmanuel Bloch, where they study localization here in a quasi-random optical lattice, so in a 1D system where you have atoms on a lattice, and then you turn on some on-site energy modulations with a wavelength that is incommensurate with the lattice. So you have some quasi-random potential in 1D, where it's also known that you can have Anderson transition. And then what they do is they have a third, so they have two parameters they can tune, which is just the hopping on the lattice. They can tune the strength of the disorder by this by shifting these on-site energies. And then they have the third parameter, which is independently tunable, which is the interaction strength. And the question they want to answer here is, well, is the localized phase robust under if you turn on interactions? And this is now in a closed system. So do you have many-body localization? And the way they distinguish many-body localization from non-localization is by looking at an initial perturbation, which is here in the density, and ask if this initial perturbation decays to zero or not. So the perturbation here consists in putting on every second side atoms into this lattice. So you start out with some imbalance where you occupy, let's say, all the even sides in your lattice and the odd sides are not occupied. And then you ask if this imbalance, as you turn on, let's say, interactions and wait for some time, if this decays to zero or not. And this is the experimental findings that they have. So you have localization. So if you turn off interactions, well, it's known that you have a transition from a delocalized extended to a localized phase at some critical value of your quasi-random potential. So this is shown here. And then the question is, well, if you turn on interactions, what happens to this transition? And here you see that, well, that's first the clean system where you don't have a localization, and once you turn interactions, the system quickly relaxes to an ergodic state where the imbalance drops to zero. And this is now experimental data for a regime where you started in the localized phase and where turning on interactions, the imbalance just remains up to the time scales they could measure here in the experiment. So from this experiment, they conclude here on the phase diagram that, well, when you're in the localized phase, turning on interactions, this doesn't destroy the localized phase. So this is, I think, very interesting recent work. Now, what is the experiment that actually motivated our work is this experiment that I will now discuss in detail in the group of Alain Spee, which was just looking at signature of localization in terms of a coherent backscattering peak. So this is a signature of localization, well, at the onset of localization. And this experiment is quite interesting because in a way it allows you to study in a very controlled way Anderson localization now as time increases. So the first experiment was done on short time scales where you can study weak localization corrections to classical diffusion. But it's clear that as you study this experimental setup on longer time scales, you should be actually able to observe now how strong localization phenomena build up in this experiment. So this is a very nice thing because this allows you to study in a controlled way how strong localization builds up, where you control parameters time. And this then motivated to look for signatures in this experiment which reflect the strong localization. This here in terms of the forward scattering peak. So this I will talk now about in quite detail. And then, so this is one part of the remaining talk. And then the second part is actually that one can just have a very simple idea how you can modify the already existing experiment in a way to, just using the great tunability of cold atom systems, which then allows you to systematically really study the onset of localization. Well, this is just a simple idea. This will be then the second part what I will talk about. Okay, so after this introduction, then let's really start with what we were interested in. So this is the experiment in the group of Alain Speth and Vincent Josse. What they did is the following. They so they managed to prepare an initial state of cold atoms with a well-defined momentum. So what they did is they trapped their cold atoms and then give this cold atom, this cloud of cold atom, an initial kick. So this is an image of your initial distribution, which now has a well-defined momentum K0. So this is the initial state you start out from, and then in the actual, Quench experiment, what they do is they release this cloud of cold atoms with a finite momentum from your trap. Then in the first step, they have to suspend this cloud against gravity by magnetic levitation. What they then do is they just switch on the disorder speckle potential, which here in this setup was elongated along one axis to mimic two-dimensional disorder. So then they just evolve the cloud of cold atoms in this disordered environment for some time t, after which they switch off the disorder potential and take again a snapshot of your momentum distribution. And as already said, so this experiment is all done at low density, so everything I'm talking about here is single particle physics. So, but it's in a way a very nice experiment because, as already said, it allows you in a very controlled way to study how you cross over from weak localization effects at the onset of localization to strong localization effects in low-dimensional systems. So you can observe the flow as time increases from the onset to strongly localized regime in low dimensions, where well, the observable is given by you start out with well-defined momentum in the initial state, you evolve this initial state under the random potential Hamiltonian for some time t, after which you look at the overlap with some final momentum state. So the observable that you use here to study Anderson localization is the momentum distribution, and the control parameter, as already said, is time. So then let's just first look at what you would expect in such a experiment if you assume just classical diffusion. Well, classically, if you start out from, let's say, your cloud with a well-defined momentum K0, you put it into the disorder speckle potential, will just, elastically scatter around into all states available by conservation laws, so here by energy conservation. So your cloud of cold atoms will just scatter isotropically around the energy shell. So after a few elastic scattering times, you will have arrived at a completely structureless configuration, which is just saying again that you have a Markovian process, so the system doesn't keep any memory of the initial state you started out from. So there won't be any momentum correlations building up in time. Now the observation by Anderson is, well, if you consider the corresponding quantum dynamics, then there's a new ingredient, which is interference, and this means that the system actually can keep memory of the initial state, meaning that now you should actually see the creation of momentum correlations, and then the question is, what are the momentum correlations signaling weak and strong Anderson localization. So to address this first, at the onset of Anderson localization, well, one can start looking in the orthogonal class, where you have, it's already mentioned, the mean, or the driving processes that localize a particle in the orthogonal class are just the singly intersecting path. Now, if you look here, a particle entering into this loop and leaving this loop will have momenta just anti-aligned, meaning that if you look at the corresponding process in momentum space, then you will find that the corresponding process should give you a peak in the backscattering direction, so you have a coherent backscattering. This is what they were after in this experiment, this first experiment by Alain Spies, Vincent Josse. So here you see now experimental data of your initial state, where you started out from a distribution with a well-defined momentum. Then they put it into the disorder speckle, let it evolve for some time t. So elastic scattering time here is about a millisecond. So you see after a few elastic scattering times, the initial peak has already decreased. The atoms start to populate the energy shell, but you clearly also see the signature in the backscattering direction, so the backscattering peak forming. So this is the leading effect, the precursor effect, or it's just, I mean, the simple weak localization correction known from disordered metals. So this is a precursor effect in the orthogonal class. Now you can ask, what is the leading precursor effect in the unitary class? So where you have broken time reversal symmetry. So as said already, if you break time reversal symmetry, the leading interference process driving localization is due to this twice intersecting path. Now, if you look at this in momentum space, you will find a correlation of your initial momentum state and the final state being aligned with the initial state. So in the unitary class, the driving process for localization should signal in a peak which appears in the forward scattering direction, so in coherent forward scattering peak. Now this has been studied in quite nice work by Kapjuk and co-workers by simulating the experiment done by Alain Spies' group. And here now you see just numerical data from the simulation. So this is a configuration after a few elastic scattering times simulating the experiment, where most of the atoms have just redistributed over the energy shell, and you have this signature, the coherent backscattering peak. Okay, I should have said this was simulation in the orthogonal class, where of course you have the leading correlation momentum space in the backscattering peak, but then you should also see the next order momentum correlation, which should then appear in the formation of the forward scattering peak, which you see here clearly after a longer time. A second peak forms now in the forward scattering direction. Now what they did in this work, they studied then the forward scattering peak using some perturbation theory and self-consistent theory for localization, and concluded that the forward peak builds up on long time scales, meaning that they build up on a time scale which is the Heisenberg time characteristic for phenomena that appear in the strongly localized regime. So this is an effect which actually becomes pronounced in the strongly localized regime. So this then, of course, raises the question, if you really want to have a full understanding, so it turns out that this is then a signature of strong localization, and if you want to have a full understanding of this, you have to do something better than just, I mean, if you want to have an analytical understanding of this, then perturbation theory. So you have to come up with some different method to try to understand and better this signature of strong localization that you would observe in this experiment. And this is actually where we got interested in. So thought this is quite a promising experiment where you could really now, in a very clean way, study a signature of strong localization effect and compare this to our current understanding of localization. So what you should really do is then you should start out with the field theory for localization and try to derive now an analytic result for the forward scattering peak. And this is what we did. So now there come like 3 technical slides, but then I will return again to results. So this is just, I mean, maybe more for people interested in technicalities. So you start out from the effective theory for localization, which is the nonlinear sigma model, the diffusive nonlinear sigma model, where, maybe I should return first, where, well, the main player in the game here is the matrix Q. So this is the sigma model in the supersymmetry formulation. So we have different formulations. Here we use the supersymmetry formulation where this matrix Q lives on some manifold which can be viewed as a sphere with product of sphere and hyperbolic with some Grassmann variables. Okay, it's not so important. The important point here to make, however, is that the structure of the sigma model is very analogous to the Hamilton function of a ferromagnet in an external magnetic field. So in this case, the player in the game is, of course, a spin pointing into some direction on the sphere, let's say, and you see the analogy here in these two expressions. So you have, say, some kinetic term in the action, and then you have a symmetry breaking term. So in the ferromagnet, of course, the symmetry breaking is just due to coupling of the spin to the external magnetic field. So this wants to align the spin in the direction of the magnetic field vector, where the strength of the symmetry breaking is just given by the intensity of the magnetic field. Now in the sigma model, you have a very similar symmetry breaking term. So this lambda here is some special matrix in this Q field manifold. So this is a term which wants to point or pinpoint this Q matrix degree of freedom to some special point on the manifold. And the strength of the symmetry breaking is given here by this parameter adder, which is the inverse time scale on which you look at the problem and the time scale measured in the Heisenberg time. So this then clearly explained what I said before. So if you have something, okay, so maybe I should first go through this. So if you look at time scales which are short compared to the Heisenberg time, this symmetry breaking is quite strong. So this means that your Q matrix actually gets pinned to some special value at the manifold. You can look just as in a ferromagnet at small fluctuations around this specific direction. So you have a way to formulate your perturbation theory by studying fluctuations around a symmetry broken let's say phase. So you have Goldstone modes, which here in the sigma model just correspond to the diffusion modes. Now, if you then, however, look at, so this would be just corresponding then to perturbation theory is a normal, just a different way to formulate your normal diagrammatic perturbation theory. But now we are actually interested in a phenomenon which builds up on a time scale given by the Heisenberg time, so which becomes pronounced on time scales longer than the Heisenberg time. So we are actually interested in a regime where now this symmetry breaking becomes rather weak, meaning that now if the symmetry breaking becomes weak, the Q matrix wants to restore its full symmetry, meaning that you really have to look at fluctuations around the entire Q field manifold. So any perturbation treatment breaks down, and what you really have to come up with is with some non-perturbative calculations. So this is then the challenging question, like how to address this regime. Well, in the first step, what we did is you can express the observable of interest, which is here the momentum correlation function. So Q is the difference between the momentum of the initially prepared state and the final state. You can express this observable of interest in terms of some expectation value in terms of this Q matrices, where the expectation value is given by an integral of the Q fields weighted by the sigma model action. And now you can study this observable first at short time scales, where you can just apply the conventional perturbation theory. So in this case, so we considered a quasi 1D system where the forward sketching peak should be most pronounced. You will find that this increases with the square root of time on the time scale given by the Heisenberg time. And then the really challenging question for us was to see how this raising of the forward sketching peak then evolves once you enter into the strongly localized regime. So, and as already said, what we did is we considered the quasi 1D geometry, and we also considered the unitary class, where actually all signatures of localization are just stored in the forward peak. So just one slide, technical slide, which is the strategy that we use to find the forward sketching peak. So first of all, you can observe that in a quasi 1D geometry, this sigma model action is very similar to the normal action of a Feynman path integral. So if you identify, okay, didn't write it here, identify your I should have written here probably a dt, like your space coordinate with some time, this gradient q squared, so this kinetic term just corresponds to, can be identified with normal q dot squared of a particle, so the kinetic term, and then this particle is in some potential, where the potential is now given by the symmetry breaking term. So this sigma model, diffusive sigma model action in a quasi 1D geometry is just very similar to a Feynman path integral, where instead of having a point particle, however, you have now some more richer, let's say, particle, which, well, coordinate is that of the Q-field manifold. But in the same way as you have a way to look at this single particle quantum mechanics in terms of functional integrals or the Schrödinger equation, you can now map the problem here expressed in the path integral or sigma model language. You can map this problem on the corresponding differential equation or Schrödinger equation, which is known as the transfer matrix equation. And there already some simplification appears, given that the potential that you consider here is very symmetric. So this means that in the Schrödinger equation, well, you can express the observable of interest in terms of a few wave functions, but all the dependency will be only on a few relevant parameters. So in a way, you have some radial symmetry in the potential, and all what you depend on is just the radials, coordinates parameterizing a hyperbolid and the sphere on this manifold. Mm-hmm. Yes. It's just so the Grassmanns you just have to, integrate out in a very controlled way to derive then the differential equations for the wave function. So the wave function and the observable just depend on the bosonic degree of freedom. Okay, so you can express this, and then you can derive the differential equation for these wave functions by integrating out, the fermionic degrees of freedom, and what you arrive at is now here these differential equations, which consist of two parts. So it turns out that, in this problem here for the forward sketching peak, you have to consider two wave functions. So one is the ground state wave function, then you have the excited state wave function, where this delta here is now the Laplace operator on the Q-field manifold, and then you have the potential, which is the symmetry breaking, which just depends again on these two bosonic variables. So, but still, these differential equations are very hard to solve, so there were not really known solutions which we could use, but there has been a very nice recent paper by Skvortsov and Ostrovsky, which showed that you can actually, by a very clever change of coordinates, map this problem of analyzing these differential equations to a 3D Coulomb problem. So the idea is, instead of looking at the problem in these two bosonic variables here, to understand these as elliptic coordinates in a 3D coordinate system. And if you make this clever change of coordinates, you will see that this Hamilton operator, which describes, which governs the Schrödinger equations here, just takes the form of a Laplacian now in 3D, in a 3D system with a 1/r potential. So it maps the problem to a 3D Laplace operator with a 1/r potential. And this is very nice, because if we use the same trick, the name coordinate representation, we can express the forward sketching peak here now in terms of wave functions which follow now this 3D differential equation. And the nice thing is that you can actually introduce the Green's function for the 3D non-relativistic Coulomb problem and express your observable that you're interested in entirely in this 3D non-relativistic Coulomb Green's function. So this is, I think, a very interesting, nice mapping, which you could apply here. And then all you need to do is, I mean, you have to look up the 3D Coulomb Green's function, which has been worked out already in the late 60s in a very compact analytic form. And then using this result, we arrive at a well, exact analytical expression for the forward scattering peak, how it evolves in time. So it's given by this function here. Well, it builds up on the Heisenberg time, which is already known. Then you can figure out that it saturates to a value which is twice the value of the isotropic background. Well, you can also work out the asymptotics now at short time scales while you reproduce the square root t dependence that you found from perturbation theory at long time. So you see that you approach the constant value as 1 over t. You can also, from this analytical solution now, work out the structure of this forward peak in momentum space. So this is now the peak at long time scales, how it's structured in momentum space. You find that it's sharp on a scale given by the inverse localization length, which is it's a sharp structure on the energy shell, which is given by the inverse mean free path. And you can also study then, I mean, the dependence on the initial state. So all these calculations were, of course, done first assuming that you start out from a really very well-defined initial state. So you can see how this saturation value of the peak now depends on an initial state that is broader. So you have some spreading of your initial state by delta k, and you find that to get a well observable signal, this initial spread again should be small compared to the inverse localization length. So there is one, I think, very interesting connection that you can actually figure out between this forward scattering peak and the form factor. So what you can find actually is that, or what can convince oneself, is that this forward scattering peak is just a Fourier, the form factor, meaning it's just a Fourier transform of the level-level correlation function. And actually, very briefly, one can see this, for example, using some eigenstate representation. So this is a forward scattering peak now using an eigenstate representation, where these alpha k are the overlaps of the exact eigenstates with some momentum state. So you see that there appear, in a way, two terms. So one depends on the statistics of the eigenvalues, one of the statistics of the wave function, if you assume that they are independent. So this is an average also over this order. You can see that the time evolution of the forward scattering peak is given by the level-level correlations. And you can also understand why the saturation value is just twice the value of the isotropic background, just by noticing that the wave function statistics in momentum space is always that given by random matrix theory independently of what is the ratio of your lengths compared to the localization length. So this is very nice. But then returning to this observation, well, the forward scattering peak is just a form factor. This means that we can also readily understand this asymptotic behavior of this forward scattering peak. So the increase with square root of time just reflects the 1 over omega to the 3/2 behavior of the correlation, level correlation function at large frequencies. Now the saturation value, 1 just reflects the self-correlation, so this is a delta function. And the 1 over t approximation to this constant value just reflects the logarithmic level repulsion, which you can understand using a simple true resonant level model. So this is, I think, very nice. And also this tells you that in this experiment, actually what you measure, I think is quite nice, is really the spectral correlations in a finite size Anderson insulator. So of course, if you have an infinite system, then you have Poissonian statistics if you're in the insulating regime, meaning you don't have any level correlations. And what this forward scattering peak manages to grasp is the finite correlations that remain in a finite size Anderson insulator. So using the same kind of ideas for the calculation, you can work out then also in the same way the correlations existing in the fine-side Anderson insulator. Now this is very nice because this also tells you that you can generalize at least the long-time asymptotics that we found for the forward scattering peak now to general dimensions, just building on like this idea of two resonant levels. You can figure out the level-level correlation function. From that, notice that the forward scattering peak in arbitrary dimension saturates to a constant value, which I mean always given by the statistics of the wave function is twice the isotropic background, and it saturates to this constant value as 1 over t with some logarithm which depends on the dimension of the system that you look at. And this actually has been checked also by some other works. So there have been more works on the forward scattering peak, interesting work, which mainly did also ran simulations. So here's now simulations, for example, on the 2D system, where you nicely see that this logarithm fits the numerical data. And this is here taken from this paper where they compared our analytical result, which is the blue curve now, to simulations, and you see that this all fits very nicely. So I think from theory this is all very nicely understood, and now it would be interesting to see if they can really measure this forward scattering peak in an experiment. So yeah, so this was the first story that we were interested in.
Actually, so this forward scattering peak, so is it the same mechanism as, is it just a way to measure mode formula in a way for AC conductivity?
So in the long time limit, yes. So it's just given by the level correlation. So the long time asymptotics just reflects, yeah.
Technical level, there should probably a connection to the model machinery to, I don't know, what Berezhinsky initially done.
Yeah. Yeah. So I mean, I think so. I mean, we just figured out this connection. So first, I mean, did some random matrix calculation. There, you actually directly see this. So we figured this out during the calculation. Now in this numeric work, they also, I mean, figured out this relation when they ran the numerics. So this is, I mean, I think this is interesting. What I really found interesting in the story also that you can really, I mean, it's a technical thing, but you can really derive an exact result describing the crossover from the weakly localized to the strongly localized regime. So, and it's an observable which should be measurable in an experiment. So it's all single particle physics, but I mean, it's still quite interesting, I think, because it's really a way now to address these kind. I mean, you can really compare now to some really nice analytical predictions. So, okay, this let's see. Yeah, this was just the first story. Now the second story that I want to tell is just a very, I mean, simple idea, so nothing really deep, but it is that, so okay, so the actual motivation was when this first experiment by the group of Alain Speer was done on the backward scattering peak, which, I mean, again, it's just, in a way, just another way to see the usual weak localization correction. However, still, when this experiment, when they published their paper, there were some comments that, well, you could also explain this coherent backscattering peak by some classical phenomenon. And then there was all this discussion, well, it would be nice to have some smoking gun evidence that this is really due to interference. And then you come to the question, well, I mean, if it's interference, you should just perturb your system, do some decoherence to see that it vanishes. But in the cold atom systems, you have kind of the problem that you don't want to do a drastic invasion into the system because you don't want to heat up the system. So that was like the situation that we knew that they were looking like maybe for some nice way to see smoking gun evidence that this backward scattering peak is really driven by localization. And then you can come up with some very simple idea using the really very nice possibilities to manipulate these cold atom systems. So in this case, to manipulate the system on very short timescales, to come up with some scheme which allows you now to study the onset of Anderson localization in a very, very systematic way. So this is the idea I want to tell about now. And this is so our proposal to study the onset of localization. And the basic observation is that, well, in this Quench experiment, what they do in the first step, they release the atoms from a trap and suspend it against gravity by magnetic levitation. And what you can see is that they can manipulate these magnetic field gradients that lead to the magnetic levitation on very short time scales. So meaning on time scales much shorter than the elastic scattering time. And this allows you to then play around with this setup by, let's say, just applying very weak changes in this magnetic field gradient. So apply some very weak pulses that do not change the path of the atoms, but will lead then to the fact that the atom, at the moment when it's hit by the pulse, will pick up a phase factor which depends on the exact position the atom is at. So this is just something that you can see, that you can realize in this experiment, and then you can ask yourself, well, can you play around with this possibility? And the basic idea is, well, yes, I mean, very simply play around. So let's see what happens, for example, if you apply a single pulse, and let's consider the orthogonal class, so where you have the backscattering peak, and see what happens if you apply a single pulse, let's say at some time t1, so at time 0, you released your cold atoms from the trap and turned on your speckle disorder potential. At time t, you turn off the speckle potential, take your snapshot of the momentum distribution. At some time t1, you apply now this field pulse. Well, you see if you apply this at some generic time, let's say obeying this relation here, then what happens is that a particle propagating along this closed loop in this direction and a particle propagating along this closed loop in this direction, they will be just at different places when they are hit by this field pulse, meaning that they will pick up different phases, meaning that this interference should be just suppressed. So you should have dephasing here in this backscattering peak. This should vanish. Now, a very special situation arises if the time between releasing the cold atoms and taking this momentum, this image of the momentum distribution, is just twice the time in between releasing the cold atoms from the trap and applying the first pulse, because then in a way you arrive at a symmetric situation where the particle propagating, the atom propagating along either way of the loop will be at the same special point when hit by the pulse, meaning that they will pick up the same phase, so you don't have decoherence and you should have actually a backscattering peak again. While if you still wait long, again, particles propagating along either way will just be at different places, meaning they pick up random independent phases, you have decoherence. So what you arrive at this very simple, setup, applying one pulse to this already existing experiment, is you should have an echo in the momentum in the backscattering peak. So one way to see this also is, well, if you apply the single pulse, you break in a way time reverse invariance. However, the total propagation time is just twice the time in between releasing the atoms and applying the pulse. You, for a short moment, reestablish a time reverse invariant situation, so you should have a revival of this backscattering peak. So this is now some result of some analytical calculation, where in one direction we map out here a region, a momentum space covering the backscattering direction. This is time, so you see this clear the signal, this echo in the backscattering peak. Now, then you can just ask yourself, well, what happens then if we apply two pulses? Well, you can play around with this. If you apply two pulses, you will find again that you should find an echo in the backscattering peak. Now, again, at a well-defined a moment in time, which depends on the two times when you apply the two pulses, but you will also find peaks now, revivals in the forward scattering peak, in the unitary and orthogonal class. And the nice thing here is that these peaks always appear at well-defined moments depending on when you apply these field pulses, and the well-defined moments are in a clear relation with the topology of the underlying path leading to this peak that you observe. So this is, for example, now result of an analytical calculation where again we map out a region, now momentum space in the forward sketching direction, and as a function of time you see clearly a nice peak forming in the forward sketching direction. So this would be due to this loop topology that drives localization in the unitary class. So you can generalize this idea, and what you arrive at is what we called echo spectroscopy at the onset of Anderson localization. Oh, this is the best wording. But so what you have here is echo signals which form in the forward and backward sketching direction that appear at very well-defined moments related to when you apply the pulses, and where the moments where these echoes appear reflect the underlying topology of the path driving localization. So this gives you a very systematic way to test the elementary processes driving Anderson localization. And that's now, I think, the nice thing about the cold atoms, because they had, I mean, the experiment already set up. So we sent this proposal to St. Jos and Alain Speer, and they already ran the experiment. So this is now the experimental result for applying a single pulse. So this is experimental data once they repeated the experiment without the dephasing pulse, where you have here the backscattering peak, and once they applied the dephasing pulse. So this is now here the experimental data showing the backscattering peak. So this is the one region here on the energy shell which maps out the backscattering direction. You see the presence of the backscattering peak. So here they applied the single pulse at 1 millisecond. And you nicely see this echo here appearing when you apply the single pulse. And they checked that this is really, I mean, the coherent backscattering echo that we are saying by, I mean, just varying the time when you apply the pulse, and you always see this nice revival at twice the time of the applied field pulse. So this then brings me already to the summary. So I spoke here about, well, I think, I mean, for theories still there's some nice things one can look at in the single particle localization problem. So if you're good in selling, you can say, well, the forward sketching peak is like a time-resolved portrait of a strong localization phenomenon with a perspective of observing using current device technology. So this is a very clear signature, which we can now really compare our understanding of single particle localization, I think, on a new level. So I think the nice thing is that you, in this experiment, have a direct observation of the level-level correlation function in a finite Anderson insulator. Now, from a technical point of view, I think that this mapping to the 3D Coulomb problem is really interesting. Here it provides us with the ability to obtain full analytical results. And then the second thing is just, I mean, a very simple idea how the already existing setup of experiment can be modified to really now systematically study those processes driving Anderson localization. So we hope that there will be more to come. And yeah, that's